Saxon Advanced Mathematics, lesson 119. I apologize if you have been anxiously awaiting the new lessons. My other students have been busy taking their final exams, so I've been caught up in that. And I have fallen a bit behind in the last few lessons here for Advanced Mathematics. But here I am to talk about lesson 119. Now, this lesson is kind of part of a continuing saga we've had of trying to nail down a strategy for finding the roots of polynomials. Now, if it's a polynomial with a degree of 2, so it's something like this, ax squared plus bx plus c, right? This is tried and true. We can solve these. Sometimes we can just look at them, and we know that we can find two numbers that multiply to this and add to that, and we can go right to the factoring. That's what we learned back in Algebra 1. It's easy, it works out great, as long as the numbers are simple. Sometimes the numbers aren't simple, and we have to do this thing called completing the square, which works every time. It's not like inspection where it only works on certain kinds, depending on what the coefficients are. Completing the square will work for everything. Downside, it's got a bazillion steps, and it annoys everyone. Even going back to the mathematicians back in the 1400s, 1500s, 1600s, they hated it too. So they came up with a new wrinkle. They said, let's have something called the quadratic formula. I call it the man-eating dragon. That has to do with a picture that one of my students once drew of a dragon who was breathing fire. And inside of the ball of fire that the dragon was breathing, my student wrote the quadratic formula. So we started calling it the man-eating dragon. It should have been the man-eating dragon's fire, but we just shortened it to man-eating dragon. Okay, so all three of these methods, quadratic formula is just a shortcut of the of completing the square. It just jumps you right to the end point. And as long as you memorize it, you're good. Those work really well. These three methods work great as long as it's a second degree polynomial. But what about higher degree polynomials? And remember, by degree, we mean the power of the highest term in the polynomial. That's the degree of the polynomial. We don't have, there is no one comprehensive method for solving. Dang it. This one we have 3, but for higher degree polynomials, we don't. Now, we do know that we do know a few tidbits. I'm going to tell you one of them. When we look at a polynomial, we look for that highest degree. That tells us the maximum number of roots that we will have for that polynomial. There might be less than that, but there will never be more. So there's a hint. That tells us something. We've known that for a long time. The number of roots is equal at most to the highest degree of the term. Here, the highest is 2. So that's been helpful. We've known that for a long time. In lesson, so these are all of the hints we have. We learned something in lesson 117. We learned how to make a list of all possible rational roots. Remember that roots can be rational numbers, numbers that can be made into a fraction. They can be irrational numbers, which means they go on with decimals forever with no pattern, or they can be complex. Okay, so those are the three different kinds of roots we can have: rational, irrational, complex. In lesson 17, we learned that we can make a list of all the possible rational roots, and then in lesson 118, we learned how to test the list to find the roots, but only for x to the third power. We can't go any higher than that. And the trick we learned in this lesson is that first you use synthetic division to break out the first piece, and then you use the man-eater, the quadratic formula, to solve it the rest of the way. That's what lesson 118 was all about. But again, it only works for the third power. So we still don't know how to find the number of, we still don't know how to nail down the number of roots for larger polynomials. This lesson is going to give us another tool that we can use to help find that. It was written by one of our old friends, Descartes, and it's called his rule of signs. Now, you may remember earlier this year we learned, I think it's the law, right? Law of sines and the law of cosines. That's the other kind of sign. That's the trigonometry, S-I-N-E-S. This is the rule of signs as in positive negatives, all right? And that's what this will tell us. It will reveal the number of positive real roots, positive, yes, real, and the number of negative real roots. Okay, so it'll break it down for us. It doesn't tell us just the number of roots, but it tells us how many are positive, how many are negative. Real, that means it includes rational and irrational. Okay, I'm going to tell you the basic rules. You're going to write them down. They're not going to make any sense to you until we go a little further. To find the number of positive roots, we're going to calculate the number of sign changes in the P of X. I know, that does not make any sense to you right now. And for the negative roots, we're going to calculate the number of sign changes in P of negative X. Don't worry, I'll explain it later. All right? So this is Descartes' rule of signs. We're going to be calculating the number of sign changes. I know that sounds weird, but I'll explain in just a minute. Oh, let me, if you need more time, pause now to write all this down. Okay, so let's explore this further and let's see how these rules actually work. Let's go to example 119.1. So, John's giving us, by the way, this lesson has 4 examples, 2 in this topic and then 2 in the next topic. All right, so we have a big fat polynomial. Let me write it down. Okay, That's big, isn't it? And so what we're trying to find, we don't have any simple way to find the roots of this equation, but we can find out the number of real roots that it has that are positive and the number of real roots that it has that are negative. So, how do we do that? We have to count the number of sign changes. And this is not a difficult process, but at first it's a little backwards in your brain. What I'm going to do is I'm going to start with this first term. And there isn't a plus sign in front of it, but I can add it if I want, right? Then the next term has a negative sign. So going from positive to negative, I can see there's a change. So I write C and circle it. So from the first term to the second term, there's a change. Now I go to the third term. That's positive. Oh, look, it changed again. So this C kind of reflects what's happening after it. That's a little bit confusing. Here we bring down a minus sign and we see, oh, it changed again. So this C reflects that minus sign. And you can see John has set this up so that, and this is minus, so there's another change. John has set this up so that there's a whole bunch of sign changes. Now, the other thing is that he told us, where's my page? He told us that the number of positive roots will be the number of sign changes in P of X. What he means by P of X is this original expression. So I can just add that right there. This is on the plastic part of my paper and it doesn't want to write. Okay, so we can say that the number of positive real roots is at most 1, 2, 3, 4, 5. Okay, now here's the thing. We said that these are the positive real roots. So that includes rationals and irrationals. Remember I said there are 3 different kinds of roots? I'm just going to write some of this down so you can see it. 3 kinds of roots. They can be rational. They can be irrational. These are numbers that can be made into fractions. These are numbers that can't, but they have long, irregular decimal points, but they're still real numbers, right? These are both reals. The third kind of root is a complex number, and that always takes the form of a plus bi, where this is the imaginary piece, right? Oh, squeezing it in. This is the third kind of root. We're saying that it's got at most 5 roots that cover these 2 kinds, but there's always the possibility that this polynomial has some complex roots, right? We've seen that in second degree polynomials. Sometimes we solve man-eating dragon and we get imaginary numbers, right? That happens. So it could happen to this as well, that it would get some imaginary numbers that would lead to a complex number when they pair up. So we have to take into consideration the fact that there might be complex numbers. Now, here's something, let me just say this too. Way back here at the beginning, we knew right here that this polynomial would have 5 roots max, and that would include real and complex. It could be either. And again, the reals can be irrationals or rationals. So that we knew back at the beginning. And we did this calculation, and what that turned up is that, yeah, we could have as many as 5 different positive real roots. By positive, I simply mean, positive number. But we want to say, is there a possibility that we have any complex? Yes, there is. But here's an interesting thing about complex numbers, or complex roots, as we call the solutions. They always come in pairs. And we've seen that when we've solved the man-eater because our complex numbers are always plus minus, right? So they always come in pairs. So that means that when we're considering this polynomial has we're refining this, the number of positive real roots is whoops, why did I write an H? Is 5 or 3 or 1. That's our final answer. We calculated a max of 5, but we know there can't be 4 because that would imply that there's 1 complex root, and we know that complex roots always come in pairs. So if there aren't 5, then there could be 3 because we subtract 2 of the roots would be complex. Or maybe there are 4 complex roots, and that would take us all the way down to 1. So the number of possible positive real roots for this polynomial is 5 or 3 or 1. Still doesn't really nail it down very much, does it? But that's okay, we're getting closer. Now we're going to calculate the number of negative real roots. Okay, so we're still in the real roots, we're just doing the positives and the negatives. In order to find that number, we're going to count the sign changes again, but first we're going to adjust the original polynomial to find the value for minus x. All right, so let's take a look at that. I'm going to copy this to the top of the next page. Okay, the p of x is that same equation that we started with, x to the 5th minus 2x to the 4th. You probably don't need to copy this. Plus x minus 2. We don't have to put the equals 0 here because we're writing it as in functional notation. So we drop the equals 0 and we keep this over here. Now we want to write the p of minus x. We basically have to change all these x's into minuses, which is going to be interesting because these exponents will make some of those minus signs go away. So what I'm going to do is for every x, I'm going to write minus x and copy the rest. Just looking to make sure I'm not making any mistakes. Plus getting a little crazy down here at the end. I'm curling off the row. Sorry, it's a little crowded. Okay, so now I have to simplify that. The p of minus x equals, okay, now of these x's, there are 5 minuses. 4 are going to pair off and disappear. That will leave me with 1, so this will be minus x to the 5th, right? Odd numbers leave us with a minus sign. Even numbers make all the minus signs go away, right? Because they pair all off. So, oh, you know what? John didn't even ask us about this. Never mind, we don't have to do this. John asked us in this first problem, he asked us only to find the positive real roots, and we did that. It's in the next problem, so never mind about this. We'll continue doing that in just a second. In 119.2, he gives us a different polynomial. I'm going to write it as the p of x. Okay, in this one, he asks us to find the negative. I was trying to find both the positives and the negatives in the first problem. I was making it too hard. So we want to find the number of. Notice we're still not finding the actual roots. We're just finding the number of negative real roots. Okay, so this is now where we have to do the same thing again. We have to find the p of minus x. So I'm substituting in, for every x, I'm writing a minus x, and I'm having to write a bunch of parentheses that are mandatory. Still have to go off the line, don't I? Okay, remember that when you make a mistake in your homework, I don't want you to erase it. I want you to just cross it off like I did. Okay, we're finding the negative roots. We're in the middle of processing the p of negative x. Again, for an odd number, we'll have one minus sign left over. For an even number exponent, all the minus signs will pair off and disappear. So this will become minus 2x to the 5th plus 3x to the 4th minus 4x to the 3rd plus 5x minus x plus 2. And you'll notice that once again, we get a really strong pattern of changing here. So we will analyze that in our next step. We're going to count the number of changes. We're starting with a minus. We're going to a plus. That means it's changing. Now we're going to a minus. We were at a plus, so this represents a change. And we can see John has set these up so that we have tons of changes. It goes to a plus 2. So once again, we have 5 changes. Spoilers, that's not always going to be true. That's just the way John has set up these particular polynomials. But that's not always going to be true. So what does that tell us? That tells us that the number of negative real roots is 1, 2, 3, 4, 5. That's the number we calculated. But we know there could be complex roots that will always appear in pairs. So we subtract 2 from this to say it could be 3 or it could be 1. The reason we have a range is because we're taking into consideration the fact that there might be complex roots, but they will always appear in pairs. So we subtract 2 and then 2 more to calculate that. Guess what? These are our correct answers. Yay. Okay, again, why are we doing all of this? We're trying to pin down the number of real roots. We're just trying to find out anything about the roots of these higher order polynomials. We cannot use our old tools. They don't work. So we're using all of these starred things, right? We're just trying to guess our way into knowing how many roots these higher order polynomials have. There is no one tried or true method, so the best we can do is guess. Okay, I'm ready to do part 2, but I have to find a fresh piece of paper. Hang on. Okay, so that is the first part of lesson 119. The second part of lesson 119 goes back to, let me tell you the name of it. It's called upper and lower bounds, which will mean nothing to you right now. But this is kind of a fun, helpful topic. Okay, remember back in lesson 116, we talked about this thing called the region of interest. And what that was an attempt to zero in on the more interesting parts of our nonlinear graphs, right? It's saying, boy, they go to infinity And those are usually just kind of plain simple lines. But where they have all their loops and curls and twists and turns, that's the part we're interested in. So let's find a way to just zero in on that. And we came up with this concept called the region of interest. You take the biggest coefficient in the polynomial, you find the absolute value of it, and then you add 1. And that represents the region of interest. But sometimes that region of interest is unhelpfully large. Okay, and John gives us a really nice example of that. He gives us this polynomial, y equals x to the 4th minus 13x squared plus 35. So what we would do is we would take the largest of the coefficients, it's 35, and then we would add 1 to it. That gives us a region of, and we write it as plus or minus, 36. That's really big, isn't it? But when we look at the graph, which John very helpfully provides for us, and notice that the scales are really wonky. This is minus 5, this is plus 5, this is 40. Our graph goes kind of like this. So we can see that even though this dimension is really long, right? It's going up here to like 35 or 36. It's really, the region of interest makes sense here. This dimension is much tighter, right? If we drew this proportionally, it would be totally skinny. So we can see that even though, yeah, 36, we need that number for this, we can zero in on the interesting part if we look at a much smaller area of the graph. That's what these upper and lower bounds do, is they help us set a more zoomed in parameter so that we can look at our picture more zoomed in rather than where the region of interest tells us to look. Sometimes that region of interest is unhelpfully large. That's what we mean. Okay, so upper and lower bounds. If you use that expression, they refine the region of interest. Okay, that's what these are good for. Now, how do we calculate them? Okay. We find the bounds using synthetic division. We sure have been using that a lot lately, haven't we? I'm going to scooch this up so you can see the end of the page very little bit. And again, these are my notes. They're not going to make sense to you yet, but this is what we're going to do. To find the upper bound, we use positive integers. And we're testing to find all signs match. Again, this will make sense in a minute. We use negative integers for the lower bound. And in this one, we're looking for alternating signs. And in both of these rules, we remember that the number 0, I'm going to put a slash through it just so you can tell that's a number. 0 can be positive or negative. All right? So as we're examining these patterns and trying to see if all, by signs I mean positive or negative, we can make 0 fit the pattern however we want. All right? So these rules we're going to use in the next part as we actually test these. So let's go on to a problem here. Get back in frame. There we go. Example 119.3 we're up to. Use the upper and lower bound theorem to find an upper and lower bound for the real roots of the equation x squared minus x minus 21 equals 0. So what they're saying is, here's a polynomial that we've graphed. It wouldn't look like this, but just pretend. We've graphed it. We want to know how tightly we can zero in. But this also relates to the other part of the lesson where we've been talking about trying to figure out some kind of information about the roots of our higher order polynomials. This one's not a higher order, so it doesn't fit, but this technique will also give you more information in that other pursuit that we've been working on. Okay, so what are we gonna do? We're gonna try to find first the higher bound. What that means is, what's the largest rational root? Rational or irrational, real root is what I want to say. What's the highest real root our number can be? Well, I gave you these weird instructions. Use positive integers for the upper bound, all signs match. Okay, what that means is we're using synthetic division. We're just gonna start with positive integers. 1, 2, 3. I'm gonna set up 6 different divisions. I know. Don't worry, I'm going to teach you a shortcut in the next example. And let's see, our pattern of coefficients is 1, minus 1, minus 21. So I'm going to use that for all of these. So I'm just going to write it in. I'm setting up 6 synthetic division problems. And we're looking for, because we're testing for the upper bound, not higher bound, the upper bound. I'll fix that. The signs need to match. So all positives are all negatives. It's not higher, it's upper, my bad. All right, so let's start dividing. 1, we multiply, we bring that one down, then we multiply and add, we multiply and add. Okay, this did not give us an alternating pattern because no matter whether this 0 is positive or negative, oh no, this isn't alternating, this is all signs match. This could be positive or negative, but that's clearly positive and that's clearly negative. So this one doesn't work. I'm gonna cross off positive 1. Remember, because we're testing for the upper bound, we don't have to test any negative integers. We know it's gonna be positive. All right, let's try 2. 2 minus 19. Nope, that one didn't work either. 3. And we can see part of the problem here, we can kind of notice this as we're going. We're not getting all one or the other. And the part of the problem is this last number is so big that even though our integer is getting bigger, it's still not big enough to overcome this big negative here. We want to turn this last number into a positive. So we pay attention to that little pattern. That's going to be useful in the next example. But right now we just keep going. 4. Okay, so we can see we've gone from negative 21, negative 19, negative 15, negative 9. We're getting there, but we're not there yet. Bring down the 1. Oh man, now we're getting really close. Hopefully, let's see what happens with our 6. Yay! See, we finally got to the positive number. So 6 is our upper bound. And what we can tell from this calculation, which yielded us this pretty pattern of all positive. They could have been all negative. That would have been fine too. But all positive tells us there are no real roots greater than 6. Okay, that helps us with our picture, right? This picture doesn't, or the The equation we used here doesn't match to this graph, but it helps you see the same idea though. The 6 and the -6 show us, oh look, it's tight that way. It helps refine the region of interest. Okay, and so now we need to find our lower bound. And the only thing that's different in finding the lower bound is that instead of using positive integers, oh here, I want to cross these off. This was the one that worked. We're going to use negative integers. Same pattern of coefficients. And I hope you're doing the synthetic division with me. If I'm going too fast, just pause me and do it yourself. You can check your numbers against me. But at this point, I hope you're really fast at synthetic division. Okay, so here we go. We're just going to start multiplying. And again, with the lower bound, we're not looking for them all to match. We're looking for, these were the notes we had, we use negative integers for the lower bound, and we're looking for alternating signs. So we're looking for a pattern of plus, minus, plus, minus, plus, minus in our result. So here we go. 1, -1, -2, 3, -18. Wait, I did something wrong there. This would be positive 2. Okay? -1 times -2 does not equal positive 3. It equals positive 2. Okay? So we do not have an alternating situation here, do we? So that one doesn't work. Let's keep going. 1. That doesn't alternate, does it? Keep going. That's -4, that's positive 12, that's -9. Still no alternating. All right. Okay, we're getting close. This is down to -1. That's very exciting. So let's try one more, but it's not that. 1 -5, that is -6. This is 30, that's 9. There it is. We finally got that alternating pattern we were looking for. We can stop. We don't have to keep going. We already know that the lower integer doesn't work, so this one works. So this tells us there are no real roots, rational or irrational, less than -5. So that tells us, another way to say this is the correct answer. Another way to say this is that the real roots to this polynomial lie between 6 and -5. My voice went crazy on that one. That's the final answer to our problem. That's the most precise way to write it. If you told me these two things, that's fine, but I really like to see it written in one single statement. Okay, so again, that doesn't tell us anything about the complex roots. That doesn't give us specific coefficients, but again, we're just trying to narrow down the solutions for these higher order roots. And again, this one isn't even a higher order, but it's helping us. Now, the only problem with this is that this is a lot of rigmarole, isn't it? That's a lot of synthetic division. That's a lot of hand calculation. Let's talk in the last example about how we could trim it down and make this a little less dramatic. Example 119.4. This is our last example. There's a third topic, but it's just a quick conversation and a look at the book. So for this one, what we're going to do is we're going to do a little bit of intuitive guessing. All right, here's our polynomial, and we're trying to figure out a little something about the real roots of this equation. We're trying to find those upper and lower bounds. Now, tricky thing right here, we're missing a term, aren't we? So we need to expand this plus 0x squared minus 21x plus 20, right? We need this term in here when we do our synthetic division. Now, let's start with, we're going to work on our upper bound first. And we know that for that one, we're going to pick divisors that are positive integers. So let's start with 1. What are our coefficients? Here they are. 1, 0, minus 21, and 20. Okay, so let's do it. 1 times 1 is 1. 1 times 1 is 1. Now we can stop right there because we can see this has messed us up, right? We need either all positive or all negative. So as soon as I see this, I stop and I say, okay, what's going on here? And what I realize is that I'm gonna need a much bigger number here. Let me write it down and then I'll tell you what I'm talking about. I'm going to need to add a bigger number here in order to turn this positive. These two are positive, so I know that's what I'm going for. I'm going for all positive. I need a bigger divisor so that when I multiply this number times the divisor, I'll get a bigger number here that I'll need to get a number here that's greater than minus 21 so that I can turn that positive. So I'm not going to try 2 and 3, and I don't really even want to try 4, but I'll try it. So what we do is we're just going to skip up a bit in the numbers that we're trying. So let's try a 4. All right? 1, 0, minus 21, 20. I know I need the same numbers. And then let's set up 5. Okay. So we're just doing synthetic division all day long. Okay, this didn't quite get us to where we needed, right? This is still a bit too small. As soon as we see that negative number, we can stop. I don't need to keep going. This is already ruined, right? So now let's try 5. Look, oh my gosh. This goes to 40. Look, there it is. This finally happened. We overcame that negative 21 that's been giving us so much trouble, and I found the pattern. So that tells me that 5 is the upper bound, okay? That means that the real roots of this equation are not going to be greater than positive 5. That's the upper bound. Okay, now we're going to try the lower bound. And we remember that with this one, let me find my original rules. Here they are. We use negative integers and we're looking for a pattern of alternating signs. These two rules are super important, aren't they, in order to actually make this happen. So again, let's skip up here too. We already know that the 1 didn't work and we skipped all the way up to the 4 and it was the 5 that actually worked. So what I want to do is I want to start, since it was positive 5, I want to start with negative 5 and see what happens. Okay, so I'm using negative 5. That's my negative coefficient, or my negative divisor, my negative integer. I need my same pattern of exponents. 1. It worked. And this goes to this, but remember, it doesn't matter. 0 can be positive or negative for our pattern. Yes, this works. However, I think that we should check -4 just to be sure we didn't skip up too much, right? So this looks good, but let's just try -4. And remember, with synthetic division, as soon as we see that our pattern isn't going to work out, we can just stop. We don't have to complete it. And there I can see, nope, that's not going to work. And so this is the lower bound. So what that means is that the real roots lie between, what did we find? We found +5 and oh, and I'm looking at the wrong example, no wonder. Okay, so there's our final answer. So what this example illustrated is that you can skip around. You don't have to try every single integer. You can use your instincts and your best guesses. Just be sure to test carefully, but you don't have to do every single integer in a row in order to test them. Okay, the last thing I want to show you is just in the book. We don't have to take notes on it. It's talking about irrational roots. We've sometimes talked about real roots, but we haven't talked specifically about irrational roots. The problem is that it's really hard to find a theorem that will give us irrational roots. The best way to determine rational roots is by using a calculator, a graphing calculator or a computer, but we can determine a little bit about irrational roots just by looking at graphs of things. And so John just wants to give us a little sneak peek, just a tidbit of that. If we see our graph crossing a line, this can be helpful in estimating our irrational roots. Let's see what he says. So imagine this picture here. It's the first value is 2, the second value is 3, and we see it crosses from positive 0.5 to negative 0.62. What John says is that if one value is positive and the other value is negative, we know that there's a value for 0 in between them, and that can allow us to estimate irrational roots that fall between 2 and 3, right? We can use this as kind of like a scale to estimate. So if it was 2.5, we'd look 2.5 and estimate. So in college level classes, calculators will aid in the estimation of irrational roots. We aren't going to do a whole lot with it other than look at the picture. That's your takeaway, okay? Just remember, irrational roots are out there. We're not worrying about them. Okay, that's the end of lesson 119. Our pursuit for the great ways to find the roots of higher level polynomials continues. We have tools, but we still just don't have a really hard and fast way to pin them down. And spoilers, we're not going to find it. The math search goes on. Okay, thank you. Goodbye.